Last minute tweaks here. All right, so this is part two kind of a presentation from spring that was quantum mechanics for fifth graders. At that time we went from about your everyday size and the world around you all the way down to the smallest things that are conceivable by the imagination of scientists and people. But this time we're going from there up all the way to the largest conceivable sizes and highest speeds. And like I said last time, these are strange ideas. This is how the world around you really works when you're not about human size and driving around at about 50 miles an hour. So we'll look at this as we go. Einstein said everything should be made as simple as possible, but not simpler. So that's my goal tonight. And all physical theories or mathematical expressions ought to lend themselves so simple a description that even a child could understand them. Of course, we don't really know who said that. Here we go. Frank, I think I'm close to something here. A equals mc squared, B equals mc squared, C equals mc squared. Things to do today. Albert Einstein. Number one, rethink mass-energy equation. 2, finalize time-space continuum thing. 3, reject statistical quantum theory. 4, work on Nobel acceptance speech. 5, get haircut. So, one of the mysteries of science explained. So what we'll look at tonight is, why did we need new physics? What was wrong with physics before Einstein came along? And different than the last talk, this really is the Einstein show. I mean, we'll hear about a few other scientists like Maxwell and like that, Lorentz, who contributed, but this really is a one-man show, which is really unusual in science. Some people have even said that the equations of relativity are about a century or so ahead of their time. It just got plopped into the world for us to deal with before we really knew that we needed them. So we'll look at special, then general relativity and see what's so special about that. And we'll look at what relativity says about the universe, and we'll see what the end of the universe may look like. We'll talk really briefly in one single slide why relativity and quantum mechanics don't get along. So why the talk I gave in the spring is a different talk than what I'm giving today. And maybe sometime in the future we'll do quantum mechanics and relativity together for fifth graders or something. I don't know. All right, so what does this relativity word mean? I mean, that's thrown out all over the place. What it basically says is that you can't tell who has the most important velocity. Now, velocity is just me moving at a certain speed like this, going in a certain direction. Probably the most intuitive velocity is sitting still. You guys are all sitting still right now, right? You're at zero velocity. So that's kind of nice. You're at rest. So once you're at rest, then you can kind of measure everything around you. There's a problem with rest. The Earth rotates over 1,000 miles per hour at the equator. And at birth, if you do this little calculation, you find out that you're moving to the east. Let's see, east is that away. At 793 miles per hour right now. I'm going to give this talk tomorrow night in Estes Park, and I calculate for them it's 792 miles per hour, so 1 mile per hour slower Estes Park, because they're just a little further north. At the North Pole, you wouldn't be moving, you'd just be turning in place. The Earth orbits the Sun at over 67,000 miles per hour, and this is going in the direction of close to overhead in the morning sky. So if you go out at sunrise and kind of look up, let's see, get my south, look up in the south, you're going up in that direction at 67,000 plus miles per hour. The solar system is going around the Milky Way at 483,000 miles per hour, basically towards Lyra, which is, we just saw that directly overhead right now. So we're going up that direction right now at 483,000 miles per hour. Our galaxy is moving at 1.2 million miles per hour towards the constellations of Leo and Virgo, which, let's see right now, Leo and Virgo are kind of that direction, I think, in the sky. So going that direction at 1.2 million miles an hour. So are you guys at rest? You're moving all over the place. So what we're looking at is pretty much puppy dog size up to the universe in size. And we've been able to measure that gravity does what it should do all the way down to about the size of a virus. Pretty small. Find out that gravity is very, 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 very weak at that size, 218 micrometers, but it's still working all the way down there. I'm going to skip that movie for now, throw it in the end, see what the time is like. Theory of relativity also relates to high energy situations. So very high velocity, high energy, high gravitation. That's what we're going to look at why. In the quantum world, molecular side down, things are odd, and when you get to very high energy, things get odd. Everything that isn't moving at our speed is odd to us. So let's go back to Newton. Let's look at this idea of moving around and having motion. And again, we have this idea that he built his physics on, that there was an absolute rest. That some way in the universe, there's a point of view where you can say, yep, I'm not moving and everybody else is. Published 3 laws back in 1687, and we still use them today. They got the New Horizons mission out to Pluto to take pictures, and so they're good physics. So let's look at these 3 laws and see what they basically say. Law 1 is an object at rest will stay at rest. An object in motion will stay in motion unless you act on it with some kind of force. So here's a little ball sitting here. If no force comes along, it's just going to sit there forever and ever and ever. If it's moving and no force nudges it, it's just going to keep moving forever and ever and ever. Okay, that's pretty easy. Law 2, a force applied to an object will accelerate it based on how much it weighs. So here's a person pushing a car. That's pretty heavy. Not going to accelerate it very much. Pushing the lawnmower, though, you can get that thing going faster, 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 faster. So lawnmowers are easy to push. That's Newton's second law. The third law, and we're going to see this come up importantly near the end of the talk when we get to general relativity, saying that all forces between 2 objects exist in equal magnitude in opposite directions. So when I'm walking along like this, I am pushing down the earth, right? Well, the earth is also pushing up on me. Take that earth, every time I step up like this or jump, the whole earth is moving the other direction for a moment. Okay, well, you guys didn't notice that. But whether you're pulling on a cable or someone else is pulling on the cable or this person pushes on that, they both move away and you don't know who did it. Here you don't know whether it's a wall or another person pushing. There was a Mythbusters episode where they smashed 2 trucks together at 50 miles an hour to smash another little car in between. And Janie said, well, that's got the force of a 100-mile-per-hour collision in between those 2 50-mile-per-hour trucks. And they got a nasty letter saying, no, it's just a 50-mile-per-hour collision. So they simulated it and they found, yep, Newton's third law is true. Even though 2 trucks were hitting at 50, it was still 50 miles per hour worth of crash. So this assumption that Newton started with is that space and time are absolute. It's this nice, big, calm background that physics happens on. And how big they are, how fast they move, how small they are, it doesn't matter. Physics is physics. And that was great until the end of the 1800s as we started to measure things more precisely. Now in the 1800s we had a scientist named Maxwell who came along and figured out how electricity and magnetism work. So he gave us equations that tell us everything we need to know about light. They were published in 1862. But there was one funny little thing that we're going to see is Maxwell's equations said something odd about the speed of light. The speed of light, you shouldn't monkey with it. And no one understood that at all. So again, that was kind of early. Lord Kelvin was another big physicist in the 1800s, sort of became the voice of science at the end of the 1800s. He was president of the Royal Society of Science. He was knighted. He said at the end of the 1800s, there's nothing new to be discovered in physics now. All that remains is more and more precise measurement. Ooh, okay, that's pretty bold. He was asked about any particular theory of gravitation. He said, no, I accept neither theory, I accept no theory of gravitation. Present science has no right to attempt to explain gravitation. We know nothing about it, we simply know nothing about it. Wow. So Newton gave us equations, but he didn't tell us what gravity was. Being able to predict it is not the same as knowing what gravity is. And Lord Kelvin sort of expressed that. Now there's something else we're going to talk about in just a second called the ether. He was asked about this ether. He said, space is continuously occupied by an incompressible, frictionless fluid acted upon by no force, and that material phenomena of every kind depend solely on the motions created in the fluid. What is this ether thing? We'll get to that in just a moment. Some of the things that were bugging physicists in the 1800s were things concerning what's called the ultraviolet catastrophe, saying that really if you heat up something, it should emit all temperatures up to an infinite amount of energy. And also objects should be able to soak up an infinite amount of heat. If you shine light on metal, like a little photocell, or electrons should always flow, but they don't. And Maxwell's equations said that the speed of light thing should be constant. But why would that be? So they had these little things that they wrote down in letters to each other, but they didn't really publicize that physics had some loose ends. In 1896, atomic radiation was discovered, and Becquerel and Curie, Madame Curie, were doing work on this. It was found that radiation levels are higher if you went up on mountaintops to the top of towers. And they weren't sure why that would be either. But if they had been able to figure out the GPS system, which they obviously could not, they would have found that it broke right away. And they would not have been able to explain that either. So there were troubles in physics, some that they knew of, some that they didn't. So let's get back to this ether. You can hear me talking because my vocal cords are vibrating and they're making air vibrate, and little waves are coming to your ears and making your ear vibrate, and that goes into your brain. And so the air is an ether that brings sound to you. Kind of nice. How can light go through an empty space unless it has something to travel in? So what physicists made up was this idea of an ether. The luminiferous ether. It was throughout the whole universe, and it helped light travel. It was a fluid. We have a little joke from that today called the Ethernet. So Ethernet cables, sort of an idea that someday this internet thing is going to be everywhere, filling the universe. So it's kind of on its way. So two scientists, again in the end of the 1800s, wanted to really measure this ether thing. And if the Earth is moving around the sun, then it should be traveling through the ether one way, traveling through the ether another way. And it can maybe measure how fast the Earth is moving by just measuring this ether. Light riding the ether should go faster as we go one direction and slower than the other. As the Earth turns on its axis, making day and night, it should be faster in the morning and slower in the evening. It makes sense. Oh, no, it doesn't make sense. So they set up this experiment using light and mirrors. Kind of looked like that on a table. It was made so they could turn it, but it was a big, heavy table, so it wouldn't vibrate if horses galloped by outside. So here's this ether that they imagined flowing through space. Here's the Earth going around. They bounced light back and forth, back and forth, back and forth. And the light interfered with itself, kind of like the way we talked about back in the spring. And if the light slowed down or sped up in one side or the other, then these light fringes and colors would change a little bit. It would be very obvious. Even a tiny change in speed would show up. And it failed. No matter what they did, day and night, winter and spring, one year and next, it never changed. They made it more precise, more exact, more bouncing of the light, and it didn't change. They tried to come up with band-aids, like, well, maybe ether drags along with the Earth, or maybe if the light is moving, then that makes light go faster and slower, and it messes up our thing, and none of it really worked. So they were sort of in trouble. Light just seemed to be light. It did things at light speed. So now we get to Einstein. Einstein was born in 1879. At age 16 in 1895, he wondered what light would look like if he were standing still. If it were standing still, if you travel at the speed of light. So if I'm in the front of a train and I turn on the headlight and I get that train speeding up to the speed of light, what happens to the headlight? Does it blob up in a bubble in front of the train and ooze around? They wanted to know. Inquiring minds want to know. Now, some books said that the Michelson-Morley experiment, which was in 1887, it's before he was wondering about this, may have fed into his thinking. But there's actually people that have done years of research trying to figure out if he knew about their experiment. And we maybe see a hint around 1902 or so from letters to his fiancée. But it wasn't until 1931 that he really said that he had heard about this and went, yeah, well, it shows you ether is dumb. So, all right, so it wasn't a big part of his thinking. He just wanted to know this answer. So there he is at age 3. There he is at age 14. There he is at 69. I guess he always puts this side to the camera. Get me on my good side. So Maxwell's equations again said the speed of light needs to be c, just the speed of light, and never 0. If you could slow light down to 0 speed, then Maxwell's equation of how light would work would only work if you were at rest. Oh, there's that rest thing again. So here you have equations that if you can play with the speed of light, only work if you're standing still. But none of us here are. So Einstein made this assumption that the laws of physics, including the behavior of light, must be the exact same for anybody moving at a constant velocity. So he's going to get rid of this sitting still thing and just say, all right, if I'm just moving at a nice constant velocity, that's good enough. Because that I can at least feel. He wanted physics to not care who's moving faster. So here's a person on a train going, I'm standing still. And this person saying, wait, hold still. As long as you don't feel like you're speeding up, you're just moving at a constant velocity. And that was good enough for Einstein. He called that a reference frame. A reference frame is anytime you're moving at a constant velocity. Thankfully, observations at the time showed that Maxwell's equations that said that the speed of light should be constant really were. It looked like the light wasn't changing. So there was no moving ether. The speed of light didn't matter whether you're moving the light quickly or not. The color of it can, but the speed of light coming out of it doesn't change. And there was even some people say, well, maybe the Doppler effect, well, that squishing of light waves as you're moving or stretching out if it's moving away from you can change the speed of light, and it didn't do that either. So none of those things were changing how light operated. So something had to give. What had to give is the distance between points themselves had to change if you're moving. Whoa, that's really weird. Here's a ball going at 0 velocity. Here's 0.3%, 30% the speed of light, 60% the speed of light, 90% the speed of light, and the ball's getting squished in the direction that it's traveling. That's called the Lorentz contraction, and there's his little equation. And if space can squish when you're moving at some high speed, time squishes too. So time slows down when you go quicker. Moving clocks run slower. Lorentz had figured that helped make physics work better. Einstein said, what if it's real? We've now measured this with atomic clocks flown around the world with satellites and interplanetary spacecraft, and we see exactly this happening. So this leap created something called space-time in special relativity. Space and time are linked together in a fabric. Here's right and left and up, forward and back, and then up and down is forward and backward in time in this little diagram. So here is Jack. Jack is a couch potato sitting still. Here's space going along the bottom. Here's time going forward, upward. Jill is going for a walk. So Jill says, I'm out of here, Jack, and takes a walk. And you can see Jill is changing position as time goes on. That's a picture of something happening in space and time. All right, so here's our first little video clip. If I can get the mouse to show here and illustrate this space-time point.
Around 1900, all of physics, and particularly Einstein, was in trouble. They couldn't figure out how anything could move. Now, before you complain that I'm exaggerating, check out this cat. You can clearly see that the cat is moving away from Einstein at a constant velocity. But do a little sliding switcheroo, and suddenly it looks like Einstein's the one moving. This is the old-fashioned principle of relativity. But the point is that the switcheroo changes relative things like position and velocity, and not absolute ones like the separation of Einstein from his cat. Now for the problem. Before Einstein was even born, physicists showed that the speed of light was one of those absolute things which can't be changed by a switcheroo. So any switcheroo we do has to keep light moving at the same speed. But then it's obvious that we can't do our sliding switcheroo at all, which means we can't explain how anything other than light can move. Okay, I spoke too soon. There is one solution. Do you see it? We were assuming that our switcheroo had to keep every slice of time at the same, well, time. But there's no law of physics that says time is an absolute thing that can't be changed by switcheroos. So if we just rotate the slices of time while sliding them, then we can keep the speed of light the same and explain how things can move too. Of course, Einstein didn't figure out this special principle of relativity in 1905. It was already done by a guy named Lorentz 10 years earlier. But Lorentz just thought that this time rotation was a mathematical trick. And it took Einstein to step in and, you guessed it, propose that time rotation is real, that time really is relative, and that consequently, simultaneous events relative to one observer aren't simultaneous relative to another. Now that's a real switcheroo of perspective.
So this is Minute Physics. These are great on YouTube, so feel free to look at those. So when you have space-time, this idea of this space-time fabric, you get another neat idea called a world line. You can look at your world line going back to the beginning of your life. Here's a spacecraft going out into space and coming around and coming back to the Earth. Here's the sun sitting still. You get to pick who sits still in relativity. We'll pick the sun this time. Here we pick the Earth. And the Earth going around the sun does this little loop-de-loop. Here's you being born and growing up and getting older and, oh, oops. So you can map this out. I even saw in physics class someone mapping a hamburger. So hamburger had tomatoes come from this country and a hamburger come from there, and the grain that made the hamburger bun came from there, and all these world lines came in, went into the person's mouth and became them for a while, and then went its own way later. So you can have fun with world lines this way. Once you get this idea down and that moving things go slower, you get to the twin paradox. Now, it's not really a paradox. The physics just tells you what happens. If you have an astronaut twin to a business person twin and goes off on the rocket ship close to the speed of light, comes back, then the person who stayed home is going to be older. The person who went very fast is going to be having a slower clock. Things that move quickly have a slower clock. So here's another video showing the twin paradox.
"60-second Adventures in Thought. Number 5. The Twin Paradox. Albert Einstein didn't have a twin brother, but he had some funny ideas of what you could do with one. He imagined two identical twins. Let's call them Al and Bert. Now, Al is a couch potato, but Bert likes to travel. So he hops into a spaceship and zooms off at close to the speed of light. That's when Einstein's special theory of relativity kicks in. It says that the faster you travel through space, the slower you move through time. So from Al's point of view, Bert's time would be moving slower than his own. To put it another way, time might fly when you're having fun, but when clocks fly, they run more slowly in relativity. After a while, Bert decides to head back, still at close to the speed of light, and returns to his brother with his holiday snaps. But when Bert arrives home, Al will now be older than his twin, which makes their double dates a lot more awkward. Although it seems implausible, Einstein just followed his theory to its logical conclusion, and it turns out he was right. This concept of time dilation provides the basis for our global positioning system, which is how your sat-nav knows you need to turn left in 200 yards.
All right, so the ultimate speed limit, and there's lots of t-shirts like this. There's another one, 186,000 miles per second. It's not just a good idea, it's a law. But we give the speed of light the c. I've already been doing that, but the c comes from celeritas, which is a Latin word meaning speed or swiftness. And it has some interesting ideas that go along with it. It takes infinite energy to get something that has any mass up to the speed of light. And if a particle is accelerated to the speed of light, it gets infinite mass. So you're not going to be doing that. You and your cat and your car is not going to go up to the speed of light. Sorry. We also see this c in E equals mc squared, which we're going to get to where that comes from in just a moment. Only massless particles can go at the speed of light. But what's interesting is at the speed of light, time doesn't pass at all. Time comes to a stop. So if you have a photon hop off of the surface of the sun and come to your arm while you're at the beach, to the photon's point of view, your arm is touching the surface of the sun. It was at the sun, now it's at your arm, instantaneous. In fact, the universe doesn't have any size at all from the point of view of a photon. That's just some of the things that special relativity tells us. All right, let's get to E equals mc squared, because that's also on a lot of t-shirts. And to do that, we need to define two things, potential and kinetic energy. Kinetic energy is energy in motion. Here's a person riding uphill, riding downhill, kinetic energy. Up at the top, he stops, takes a drink. That's potential energy. He's about to go, wah! Potential energy can also be chemical. It can be stored in this dynamite and then boom, turns into this big explosion. So that's kinetic. So when you're dealing with things that go faster and time and space change, it also changes the idea of mass and it changes your idea of energy. And so to figure that out, we had to work with energy and kinetic energy of anything, no matter who's looking at what, and explain where the energy goes. And from that we get E equals mc squared, which another great video following the earlier one will do for you.
In mid-1905, Albert Einstein derived what is now the most famous equation in the world, E equals mc squared. But he didn't just write this down out of the blue. It followed directly from his paper on special relativity that we talked about in last week's video. And here's how he did it. Suppose you're watching a cat float freely in empty space, when suddenly it emits a flash of light in all directions. The light carries away some energy, we'll call it E. So by conservation of energy, the cat must have lost energy E. But since the light was emitted symmetrically in all directions, it won't have changed the cat's velocity. So where did the energy for the light come from? Never mind that now. Let's imagine you get bored and zoom off in a spaceship in the middle of the experiment. But from your new perspective, you're sitting still in your spaceship, and the cat is the one moving past outside the window. Therefore, you'll calculate that the cat has some kinetic energy, that is, energy of motion. And when you see the cat emit the flash of light, you'll again measure that its energy decreases by the energy of the light. Except now that you're moving, special relativity tells us that time passes at different rates for you and the cat, so you'll measure a different value for the frequency, and thus energy, of the light. This is the relativistic Doppler effect, and for our purposes, it amounts to multiplying the energy of the light by 1 plus your velocity squared divided by twice the speed of light squared. So to recap, if you take off at velocity v, you'll see the cat gain some kinetic energy ke1, then at the flash, you'll see the cat's energy decrease by e times 1 plus v squared over 2c squared. On the other hand, if you wait, you'll see the cat's energy decrease by e, and now when you take off, you'll see it gain kinetic energy ke2. But this is silly. You never touch or otherwise influence the cat in either case, so we should get the same total energy at the end. Rearranging, we see that the kinetic energies before and after the flash must be different. And the kinetic energy of an object is 1/2 of its mass times its velocity squared. But we know that the velocity was the same in both cases. So in order to account for the difference, the cat's mass must change when it emits the flash of light. Now, if we cancel things out, you can see that the change in mass of the cat must be equal to the energy of the light emitted divided by c squared. Or, as you've heard before, E equals mc squared.
That'll be on the test. I want everybody to be able to do that later. All right, so that's everything about special relativity. To recap, the laws of physics are the same no matter how you're moving. Clocks and rulers act strangely, so the principle of relativity is always true. The speed of light, c, is an absolute. There's no standard now in the universe. We get this idea of space-time, and Lorenz's little term shows us how space and time contract. Okay, that's great. This fixed how those particles from space, those radioactive particles, can last longer. They're going very fast, so they made it deep into the atmosphere. Particles in accelerators can travel longer than they should also. And special relativity, looking at 2 times the energy, gives us E equals mc squared. Is that the end of the story? No, because this is special relativity. Special relativity happens where energy is only associated with motion. There's a cat in space. There's no gravity. Oops. What are we going to do with this gravity? How do we get gravity in here? So special relativity is special because it only has everybody moving at a constant velocity. So gravity came, at least an expression of gravity came from Newton 400 years prior. Einstein really wasn't worried about these oddities that we saw earlier. He just wanted to figure out how space-time explained how gravity works, and that's what he worked on. His next big assumption that led to this was called equivalence. He assumed here that the force of gravity was something you couldn't tell different from any other form of acceleration. So here's gravity pulling down. Here is a car accelerating. If you're in the car, blindfolded, you don't know if someone stepped on the gas or if the moon just snuck up behind you and started pulling you back into your seat. There's no way to tell. The best experiments show in 1 part in 14, 10 to the minus 14, that these two are the same. And we're got an experiment this year that should push it even further. So the main outcome of this in general relativity, which came out in 1915, is that there is no gravitational force. What? I came here to hear about gravity. No, gravity just comes from the curvature of this space-time stuff that we're in. Let's see this. Now this one I'm narrating. So let's look at an apple on a tree in Newton. So here it is, nice little apple. And, oh, come on, mousey. So with Newton, you got gravity pulling down, you got the branch pulling up. That's pretty simple. And if you just sit there for a while and watch the apple, it just stays on a tree branch. Gravity pulling down and the tree branch pulling up. What's easier than that? All right, it's fall. And suddenly the apple breaks free of the branch and falls to the ground. So the green branch force goes away and down goes the apple. All right, that's pretty simple. Boring. In Einstein, though, it's curvature of space-time that's doing this. Okay, so there is no force of gravity. What you have is, for the apple to be hanging on a tree, it's just the tree pulling up in space-time. Okay, come on, let's get going. It's supposed to be a grid here that didn't show up. That's really strange. Then when you let go, the apple goes in a straight line. There is no force on the apple. The apple is in weightlessness. So here's a Newton, down goes the apple. In Einstein, the only force is the tree until it breaks free, and then the apple goes in a straight line. There's the grid. It's just not showing up. I guess it's kind of bleached out on the projector. So just about the same physics going on, but we've gotten rid of gravity. The feeling that you have that is gravity is just your body trying to go in a straight line in space-time. So in 3D, the warping of space-time around the Earth kind of looks like that. The stronger gravity goes, the more time slows down. So the GPS satellites are both going quickly around the Earth, and they're in less of a gravitational field than you are down here. Time is going a little slower in this room than it is up in space above the Earth or out between the galaxies. And the stronger the gravity is, the more squished space gets. It's just like what we saw in special relativity with high speeds. So here are the equations of Newton. Here's Einstein's equation, and I'm going to color code these. Here's force in blue. Curvature of space-time is in blue. Both equal to a constant, which is g. There's constant with some numbers, that's green. And then you've got the mass and the distance between the masses. Here you've got how matter is distributed in space. It's the same thing, it's just a lot more complex for Einstein. So the force of gravity is just the curving of space-time. Remember, the c, though, is a certain speed limit. It's that speed limit sign that I showed. If you assume that speed is infinite, then everything goes back to Newton. So that's kind of nice. So what are the things that Einstein's general relativity fixed? Well, there was corrections to how Mercury went around the sun. We detected the errors in 1859, and Newton said it should be this big of an error. Real was 43, and general relativity predicted that exact number, 43 arc seconds every century. He also predicted that light would bend around big things like the sun or planets or black holes. Newton gives half of the prediction of what we should see. Arthur Eddington measured it in 1919 off the west coast of Africa. We almost had that experiment done here, the Chamberlain Observatory in downtown Denver, but it was cloudy for that eclipse. That turned Einstein into a rock star once they got this picture and showed that his prediction of how much the light bent around a big, heavy thing was correct. That led to how big clusters of galaxies bend the light of more distant galaxies behind them around it. Here's a galaxy behind this nearby cluster of galaxies, and these are all smeared out images of the same galaxy, like a big lens in space. He predicted gravity waves, and we're spending a lot of money and improving instruments right now to try to find waves in space, just like sound waves or light waves. Looking for those still. He predicted something called frame dragging. If you put your hand in water and swirl it around, the water starts to swirl with your hand. Right there. And the Earth turning, or the sun turning, will make space-time swirl around too. And then from 2004 to 2010, we detected that with satellites. We had guesses that we could have something like a black hole under Newton's physics. But once we had general relativity, we had equations that could explain how black holes would come into existence. And we detected the first X-ray black hole candidate in 1964, Cygnus X1. Should be a big one in the middle of our galaxy in most galaxies, and here's the X-ray source in the middle of our galaxy. Whoa, go back. There's no easy way to make it go back unless I go click. Here's gas clouds zooming around the black hole in the middle of our galaxy. And, oh, that's going forward. And he also predicted that gravity, because time is going slower down there, would slow down light and redshift it, just like motion does, with special relativity. And that was measured in 1925 and 1959. He did make a little goof, though. He saw that his equations predicted that the universe should either be expanding or contracting. And he didn't like that idea. To everybody in science at the time, the universe was unchanging. So he put a little fudge factor in here called the cosmological constant that fixed that, made the universe not expand or contract. Edwin Hubble, though, made observations, plotted galaxies and their speed, and saw that all the galaxies out there were moving away from us and each other, just like dots on a balloon blowing up. Einstein said, oops, and admitted that was a blunder. So that brings us to the universe itself. No, not that universe. This universe. With an expanding universe, you can run the clock back in your imagination and see that everything once came from a single little point somewhere in some when. It's everywhere, but it's some when. And that gave us the Big Bang model of the universe. And then the question was, what's going to happen to the end of the universe? Is it going to bang and then go for a while and then crunch? Is it going to bang and then continue on forever? Or is it going to bang and just keep expanding and kind of chill out and go cold someday? Well, in the late 90s, we discovered something new called dark energy. In the Big Bang, there wasn't any measurable dark energy, but now it's 72% of the mass energy of the universe, and it's increasing. This looks a lot like Einstein's cosmological constant. We're not sure. We don't exactly know how this operates yet. But maybe he was right even when he was wrong. That's nice to be that way. In one model of the cosmological, well, not cosmological, but of dark energy, is that the dark energy will keep increasing until it starts to pull galaxies apart 22 billion years from now. So 60 million years before what's called the Big Rip, the Milky Way gets torn apart by the expansion of space. 3 months before the end, the solar system gets pulled apart. 30 minutes before the Earth explodes, and then 10 to the minus 19 seconds before the Big Rip, atoms get ripped apart, and everything is pretty much over then. So we might actually, because of observations of dark energy and Einstein's general relativity, know that the entire universe lasts about 13.7 plus 22, so 35.7 billion years from Big Bang to now to the Big Rip, where everything gets destroyed. So the Big Rip universe is added to our picture here. All right, there's still a lot of problems out there with relativity. Quantum mechanics and general relativity don't fit together, so I might make that some talk later. We don't have what's called a quantum theory of gravity yet. People are working on it very hard. In the Big Bang, when everything is smashed in a little point, how do you get out of that? How do you go from everything in the entire universe and something smaller than that and get it out into this big, huge universe that's around us right now? And in black holes, what happens to gravity when you get down to this little point in the middle where all the mass is concentrated? Stars, or millions of stars worth of matter, smashed back down to an infinitesimal point. General relativity can't handle that. How does gravity work around just normal quantum particles like a proton, an electron? We don't know. They don't, like I said back in the spring, they don't actually have a point existence. They have sort of a wave existence and a particle at the same time. And time is used differently in general relativity and quantum mechanics. Quantum mechanics doesn't have time dilation happening. So we don't have these two big successful theories talking with each other yet. Still, trying to put them together has made amazing advances. Einstein, again, the same year he came out with special relativity, explained that light hitting metal problem and basically started quantum mechanics going and showed us how to make photocells. He was a smart guy. That's where he got his only Nobel Prize, was from figuring out the photoelectric effect. E equals mc squared explains how nuclear power works and the energy source of stars in the sun. Nuclear fusion and nuclear fission. Before that, they really didn't know how long the sun would last. If it was made of coal, you probably had about 100,000 years. I don't know where you get that much coal. Higgs boson works with some of the mass source of the universe and works at it from a quantum approach. Stephen Hawking tried to stick general relativity together with quantum little particles popping up in empty space and came up with Hawking radiation and showed us that black holes will eventually evaporate. So anytime you make some progress in getting these two theories together, cool stuff happens. So in the future, I'll do a talk about nothing. The physics of empty space. We'll talk about those little particles that come and go at the edge of black holes, and space-time, and forces in space. We'll talk about how you're smarter than artificial intelligence, gravity for the masses, information and reality. These are things that I'm working up right now. So, is that a crack in Einstein's theory of relativity? Nothing's perfect. So, all right, any questions? I do have some books up here if you want to look at where you read more on this. Most of the talk came from this book, Space-Time and Quanta by Roger Mills. Follows his approach really closely. All right, any questions? We got deep and we pulled it back out. Yes, go ahead.
I was interested in your talk at the beginning there, John, about the speed and finite speeds. And I just read an article about that they're trying to use about the microwave background.
The cosmic microwave background radiation.
Figure out what our velocity through in the universe is.
Right. Yeah, I had that as was the last line. It's like 1.6 million miles per hour in the direction of Leo Virgo. So using the Doppler shifting of the leftover glow of the Big Bang, we can see that we're kind of going in one direction.
Oh, that's what that's,
yeah,
that's
that's that one.
Sorry,
Yeah.
I missed that. Yeah.
No, that's good. So, yes.
What theory of the end of the universe are you most inclined to believe?
The latest I've seen is the Big Rip is not necessarily the favored. It does look more like the Big Chill. Another names for that is heat death or entropy death. The universe just keeps expanding. Things get further and further and further apart, further apart, until you've got one atom per megaparsec, cubic megaparsec. So just emptiness. So way before that point, black holes will have evaporated and popped. So you'll have flashes of light some 10 to the 200 years from now. Black holes will be popping all over the place, but life will be done because life needs energy to be flowing from one place to another. You need chemicals going from one place to another, heat and no heat over here. Even your car needs more heat inside and less heat outside. Your car is more efficient in the winter than it is in the summer because there's a bigger temperature change in the winter. But in the distant, far-flung future, there won't be any great temperature differences. So everything will just run out.
So you believe in an end to the universe?
Oh yeah, it's not going to keep on going. Yeah. In fact, I think I've heard that the bulk of the available hydrogen and helium from the Big Bang has already been spoken for in stars in the universe. So everything is kind of already in sort of a later stage of being processed. So even if none of the expansion stuff was happening, we would run out of the primary fuel, hydrogen, that fuels the stars. Yeah, when they explode, they throw out heavier stuff that they create. And each time you have a lower percentage of hydrogen and it's spread out more and like that. So buy your real estate now. So, yes?
Now, would that preclude going back to another Big Bang somewhere else in the universe, another universe?
Yeah, there's hints in the brain theory part of string theory that at a certain super low density, that sort of a parallel dimension to ours, it might even be figured into what's called dark matter, or how gravity itself works, really theoretical there, might touch the whole universe, start the bang over again. In that model, you don't have a big bang that's everything in a point. The entire universe erupts with energy and then expands really quickly and cools, and new galaxies and stuff form. From what we see in general relativity in the Big Bang here, everything that you're made of and all the energy around you is just borrowed from gravity anyways. This is a big bank debt that we took a loan from gravity and then made tables and observatories and planets and stars out of it. So eventually we pay it back. So, yes?
So could you describe a little bit the infinite expansion after the Big Bang, which would appear to violate infinite energy required to accelerate things and actually faster than the speed of light?
Yeah, right after, in the very first tiny minuscule fraction of a second after the bang, nothing was happening right away. And then we have a purely hypothetical particle called an inflaton. I don't have an inflaton in my hand, I don't think. That helped expand empty space much faster than the speed of light, in a way that it acts like the dark energy expansion does now. But I've never heard anybody link the two directly. But with the inflaton, it's empty space that's expanding, and the appearance of particles or points in space connected to stuff seem to be going faster than the speed of light as they look at each other, but they're not really moving. It's empty space. Yeah, space itself is expanding. So it doesn't violate the speed of light speed limit. In fact, around us, around the universe, beyond the Big Bang glow that we see, 13.7 billion light years back in time, not light years back, 13.7 billion years back in time, there's a bubble beyond that in which we can't see anything beyond. And so that's parts of the universe that exist. You could have planets and galaxies and everything, but they appear to be going much faster than the speed of light away from us, so we can never get information from them. And someday that bubble may close all the way down inside the universe that we see, all the way down to around our galaxy. That's another model of the end, that there's just darkness around the Milky Way, or the Milka Media, with the Andromeda merging with us in 5-6 billion years. And so future astronomers wouldn't have a background radiation to look at. They wouldn't have other galaxies to look at either. And that's due to the expansion as well. So it just gives the appearance that things are going faster than the speed of light and you can't see them anymore. Yes?
Okay, so how are there light years if there isn't any time at the speed of light?
That is an excellent question. And in fact, where the edge of the universe, the observable universe, is as it appears and where it is right now are different because of your question. So we actually, just like picking rest, saying I'm at rest right now and you guys are moving, we pick an arbitrary point that we want to measure. We like our sun, we like our solar system, we like our galaxy, and we kind of pretend that we're the ones who aren't moving. So it is based on sort of an arbitrary spot that we pick, a reference frame that we like.
Okay.
Yep. Excellent question. That's very insightful. Any-
Thank you, John.
Thank you.